Hello guys, trust you're doing fantastic. In today's video, we're going to be talking about direct conversion method. So we're going to be converting octal number system to binary number system. Alright, so let me explain a few tips to you. In octal number system, we have a total value, a digit of 8, beginning from 0 down to 7. Now, in this situation, we can say that the minimum number in octal number system is 0 and the maximum number in octal number system is 7. Now, we need to represent these values in bits, in binary bits. The first thing we need to realize is how many bits can we represent octal number system values in binaries. Now we need to consider something which is very important. We need to look at the maximum digit. The maximum value in octal number system is 7. So therefore, whatever representation in bits we need to have should be less than 7. Should not be greater than 7. So in this case, for we to have an accurate representation of octal number system values in binary bit, we need to consider this cheat, okay, this formula where we have 2 raised to power 0, 2 raised to power 1, and 2 raised to power 2. Now 2 raised to power 0, it's going to give us 1, 2 raised to power 1 is going to give us 2, and 2 raised to power 2 is going to give us 4. Now, how does that relate to the values, the digits we have in the octal system? Now let me explain that. Now if you consider 2 raised to power 3, this is going to give us 8. Now what that tells us is that the value 8 is greater than 7. So it means that the minimum number of bits that can be represented in octal number system needs to be 2 raised to power 2, which will be 4. So this is actually less than 7. Alright, so 8 is not less than 7, it's greater than 7. So we cannot have 2 raised to power 3. So we need to move to the next lower value, which is 2 raised to power 2, which will give us 4. So in that case, that is why we have 2 raised to power 2, which is 4. So it means the maximum amount of number that can be used to represent, or the maximum amount of bits that can be used to represent octal number system is 3 bits. So we have 3 bits binary to represent octal number system. Now the next step is to determine the values of the bits. Now since we have 3 bits, so for 0 we're going to have 0, 0, 0. So it's 3 bits of zeros. Now to represent 1, this is 1. To represent 1 in binary bits, we're going to have, under this part where you have 4, we're going to have 0. Under the part where you have 2, you're going to have 0. And where you have 1, you're going to have 1. It means you can find 1 under this part. So in a nutshell, the binary bits that represent 1 in octal number system is 0, 0, 1. Using this code 421. Now let's find 2. Now 2, equivalent of 2 in binary bit is going to be, under 4 you're going to have 0. 2 you have 2, which is the same, you're going to have 1. It means it's on, it's yes. And then where you have 0, 1 rather, you're going to have 0. So in this case, what you have 0, 2, 0, means you have 2. Now for we to represent 3 in the binary equivalent, we're going to have, under 4 we're going to have 0. Now what makes up 3 is going to be 2 and 1. So it means 2 is going to be on, 1 is going to be on. So in this case, when you sum this up, you're going to have 3. Now for 4, we're going to have 4, this part, under 4 it's going to be on, that's true. And then the other value is going to be 0, 0. So therefore you have 4 equivalent representing 4. Now for the case of 5, it means we're going to turn on 4. So for the 4, you're going to have 1. Then for 2, you're going to have 0. And then for 1, you're going to have 1. Under 1, it means true. So when you sum them up together, 4 plus 1 is going to give you 5. Now for the case of 6, it means 4 needs to turn on, which is true. 2 needs to turn on, which is true. And then 1 needs to turn off, which is 0. So it means if you sum them up together, 4 plus 2, it's going to give us 6. Now for we to derive 7, it means everything is going to turn on. 4, it's going to be on, which is true, 1. 2, it's going to be turned on, which is true. 1 is going to be turned on, which is true. So if you sum everything up together, 3 plus 2 plus 1 is going to give us 7. So this is how the equivalent in binary bits is derived. Alright. So let's take this first example that says 64 base 8 equal to x base 2, find x. Now we're using the direct method, which is very easy. So all we need to do is to assign the binary bits individually to each digit and then combine them together, and then we can get the result. Now remember, this is octa to binary. Now the relationship between octa to binary is 3-bit system. Alright, 3 bits. And then 3 bits we have to use the formula known as 4, 2, 1. So in this case, for which, let's go back to the question. Now you have 6. Now for we to get the equivalent of 6 in binary bit, it means 4 needs to turn on, which is true. We assign the value 1. 2 needs to turn on, which is true. We assign the value 1. And then 1 needs to turn off. Okay, so we assign the value 0. So if you sum this together, you have 4 plus 2 is going to give us the 6 that you have here. So for 4, for we to get the equivalent in binary bit for the digit 4, all we need to do is that 4 is going to be turned on, which is 1, and then 2 and 1 is going to be turned off, which is 0, 0. So that is why we have 1, 0, 0. Then you put them together, you have 1, 1, 0, 1, 0, 0. So this is the answer. So 64 base 8 is equals to 1, 1, 0, 1, 0, 0 base 2. So this is how simple it is for you to use the direct method to convert octa number system to binary number system. Now let's consider another example with decimal point. So you have 64.25 base 8 equal to x base 2, find x. Now all we need to do is to realize that the equivalent in binary bit of octa number system, it's represented using 3-bit 4, 2, 1. Alright, so this is 3 bits. Now in this case, since we know this, all we need to do is to find the equivalent of digit 6 in binary bits. So we're going to have 110. This will give us 6, and then in the case of 4, it means 4 is going to be on, then the rest is going to be off, 0, 0. Then you have dot. For 2, it means we're going to have 0, 1, 0. So it means we're going to have 0, 1, 0. Then for 5, it means we're going to have 1, 0, 1. It means 2 is going to be turned off, so you're going to have 1, 0, 1. So you bring all of this together, so we're going to have 1, 1, 0, 1, 0, 0 dot 0, 1, 0, 1, 0, 1 base 2. So this is how easy it is to use the direct method to convert octa number system to binary number system. Alright, so let's consider a scenario where we need to convert binary to octa number system. Now the question says, now let's consider an example where we have to convert binary to octa number system. Now the example says 1010.11 base 2 equal to x base 8, find x. Now this is a scenario where we have to apply a technique known as 0 padding. Alright, so we have to pad a situation like this. Now I'm going to explain to you what we are going to do in this case. Now we need to group these values since we know that we need 3 bits to represent octa number system. So in this case, we need to group the digits on the left hand side in threes, in the group of threes, so that we'll be able to represent the binary number system in octadecimal number system. Now the rules for zero padding is this. We need to start grouping from the right to the left. What this means is this: the part where we have the values before the decimal point, we need to group from right to left. So wherever we have a situation where we don't have a complete grouping, we need to introduce what we call zero padding. We need to add zeros for we to have a complete group of 3. Then the digit after the decimal point, we need to group from left to right. And in a situation whereby we don't have a complete digit of 3, then we need to pad with 0 to ensure that each group contains 3 digits. Now let's proceed in solving this example. So we consider this value 0, 1, 0, and then we group from right to left. So we need to group in threes. Now if you notice, you have 1, 2, 3, 3 digits, 3 values in one group. So we need to group in threes. So we have this as a single group. Then we have 1 left. So in this case, we need to introduce padding, 0 padding. So we need to add 2 zeros, this 0 and then this second 0, so that we can have 3 digits in one group. So in this case, we have 2 groups on the left hand side before the decimal point. Now let's go over to the values after the decimal point. Now we have just 1, 1. So if we need to group, we need to start from left to right. So if you notice, we only have 2 values. So we need to introduce 0 padding so that we can have 3 values in a group. So that is why we introduce this 0, so that we can have 3 values in a group. So we need to decode this binary bits. That's all we have. So in this case, 0, 0, 1, it's going to represent, when we have 0, 0, 1, it means it's going to represent 1. So that means 1. So that is why we have 1 representing this first group. Now for the second group, we have 0, 1, 0. Now if you check this code, we have, when you have 0, 1, 0, it means the value is going to be 2, and that is why we have 2 representing this group. Then you have the dot. Now where you have 1, 1, 0, it means when you check the code, when you have 1, 1, 0, it means you have 6. So in this case, you have 6 representing this group. So therefore, x will be equal to 1,2.6 base 8. So this is how simple to calculate this example. Alright, so let's consider this scenario of converting hexadecimal number system to binary number system. Now, just like we said previously, we have the relationship between octa number system and binary number system. Also, we have a relationship between hexa number system and binary number system when we talk about direct conversion method. Now the rules applies just like the octa number system conversion to binary number system. The maximum number of bits that can be represented in binary coding is 4 bits. And this means that 2 raised to the power n should be less than 15. Now I'm going to explain to you this formula in a bit. Alright, so now we understand that hexadecimal number system contains both numerical values and alphabet. Now you have 0 all the way to 9. 0 to 9. And then we have the alphabet, which runs all the way from A to F. Now, if you notice that the minimum value in the hexadecimal number system, the minimum value is 0. And the maximum value in the hexadecimal number system is F, which is 15. Now, remember the value or the formula I stated here. I said that the 2 raised to power n should be less than 15. So, in order for we to represent hexadecimal number system in binary coding, the maximum number of bits that needs to be represented should be 4 bits. It means 8 is less than 15. Now, the value 16 is greater than 15, which 15 is the maximum value in the hexadecimal number system. So therefore, the rule says that 2 raised to power n, which represents the numbers of bits that should be used to represent hexa number system in binary coding, should be less than 15. Now, if we take 2 raised to power 4, that's 16, which is greater than 15. So therefore, we need to take the next lower value, which is 2 raised to power n. So in this case, 2 raised to power 3, which is equals to 8. So in this case, that is why we have chosen the maximum value to be 2 raised to power 3. So 2 raised to power 3 is going to give us 8. 2 raised to power 2 is going to give us 4. 2 raised to power 1 is going to give us 2. And 2 raised to power 0 is going to give us 1. So in this case, we have 4 bits code. So it means for hexadecimal number system, the maximum number of bits that can be represented in binary coding is 4. 1, 2, 3, 4. So this is the 4 number of bits. So this is how we derive the relationship between binary number system and the hexadecimal number system. So we're going to use the same knowledge to convert hexadecimal number system to binary number system using the direct method. So now that you have an idea of what we have done, it's okay for me to take you through how these values are being derived. Now let's begin with the first one, which is 0. Now it means for 0, all the codings, the bits is going to be 0. Now for value 1, it means every other value, 8, 4, 2 is going to be 0, and then 1 is going to be on, which is 1, saying is true. It means we can get 1 using this binary bit. Now for we to represent 2 in binary bit, it's going to be 8 is going to be 0, 4 is going to be 0, and where you have 2, it's going to be on, which is true, and then the other value is going to be 0. Now for we to represent 3 in binary coding, it means 8 is going to be off, 4 is going to be off. For we to get 3, it needs to be 2 plus 1 to give us 3. It means that 2 and 1 needs to be on. So that's why we have 1, 1. Yeah. Now, the same thing for 4. It means 8 is going to be off. Only 4 is going to be on. The others will be off. Now, for we to derive 5. So it means we need to have 4 and 1 on, which will give us 5. 4 plus 1 will give us 5. So in this case, we're going to have 8 off. 4 is going to be on. 2 is going to be off. 1 is going to be on, so that when we sum both of them together, 4 plus 1 is going to give us 5. So the same thing we're going to do for the rest of the digits. So if you follow through, it's going to be the same principle. 6, you have 0, 1, 1, 0. For 7, you're going to have 0, 1, 1, 1. So it means if you sum up everything here, you're going to get 7. So you have 4 plus 2 plus 1, you're going to get 7. So for 8, only 8 is going to be on. The other is going to be off. For 9, 8 is going to be on. 4 and 2 is going to be off. 1 is going to be on. For 10, you're going to have 8 on, 4 off, 2 is going to be on. So that when you sum up together, 8 and 2, you're going to have 10. This is going to be off. So the same thing for 11. The same thing for 12. You have for 13, the same. 14, the same. 15, the same. So for 15, everything is going to be turned on, such that when you sum everything together, 8 plus 4, 12 plus 2, 14 plus 1, 15. So you sum everything together, you're going to get 15. So this is the simple explanation how the binary equivalent was derived. Now let's consider the simple example. Now it says 64.25 base 16 equal to x base 2, find x. Now all we need to do is to represent this digit individually in their binary codings, in binary bits. Now since we know that the relationship between hexadecimal number system and binary number system is 4 bits, which is the same as 2 raised to the power 3, 2 raised to the power 2, 2 raised to the power 1, 2 raised to the power 0. Then we have 8, 4, 2, 1. So in this case, 6, we're going to have 0, 1, 1, 0. That's why we got 0, 1, 1, 0. Then for 4, we're going to have 0, 1, 0, 0. So we have 0, 1, 0, 0. Point. For 2, we're going to have 0, 0, 1, 0. So we have 0, 0, 1, 0. For 5, we're going to have 0, 1, 0, 1. That's why we got 0, 1, 0, 1. Now put all of these values together. X is going to be 0, 1, 1, 0, 0, 1, 0, 0 dot 0, 0, 1, 0, 0, 1, 0, 1 base 2. So this is how easy it is to use the direct conversion method to convert from one number system to another number system. Alright, so let's consider a situation where we have to convert binary number system to hexadecimal number system using the direct conversion method. Now let's take this for example. It says 10010.1101 base 2 equal to x base 16, find x. Now in this case, since we know that the relationship between hexadecimal number system and binary number system is represented in 4 bits binary coding, so in that case we need to group this binary equivalent, we need to group this binary digit into a group of 4. And in a situation whereby we don't have a complete group of 4, we need to introduce what we call zero padding. Now, to apply this technique, we need to consider the digit before the decimal point and also the digit after the decimal point. Now, for the digit before the decimal point, we need to group from right to left. So we need to group from right to left such that in each group we should have 4 digits. Now let's begin. Let's start from right to left. We have 1, 2, 3, 4. So it means this belongs to one group. Alright, so this belongs to one group. 4 values in one group. Now we have one value left. So in this case, we need to introduce zero padding so that we can have 4 digits in the group. So we need to introduce 1 0, 2 0, and 3 zeros. So in this case, we have 4 values. So therefore, we can group all of these digits together. So it means we have 2 groups now. Alright, let's go over to the values after the decimal point. Now, in this situation, we have to start grouping from the left to the right. Alright, so let's count 1, 2, 3, 4. So it means we have a complete 4 values in one group. So it means this belongs to one group. So we need to express the values out. So we need to represent these values in hexadecimal number system. So in that case, this is what we're going to get. Now we know we have 8, 4, 2, 1, which is the 4 bits binary coding that is used to represent hexadecimal number system. So in this case, since we have 0, 0, 0, 1, so it means in this case we have 8 will be 0, 4 will be 0, 2 will be 0, we have 1 will be on, which is true. It means this coding represents 1. Now for the next group, we have 0, 0, 1, 0. it means in this case we have 0, 0, 1, 0. So it means that represents 2. So you have the dot, decimal point, and then the next value is 1101. So let's see what that is going to give us. If we have 1 here, that is 8. We have 4 is on, 0 is off, 1 is on. So if you sum these together, you have 12. Add to the last value, which is 1, that's 13. So it means this group will represent 13. Alright, so in a nutshell, we know that in hexadecimal number system, it consists of both numerical values and alphabet. Now we need to represent, since this is 13, what is the alphabet equivalent of 13 in hexadecimal number system? So that is going to give us D. So we're going to represent our answer this way. We're going to write 12.D base 16. Always, you need to ensure that you must always change it. Once the value is greater than 9, once it's higher than 9, it means you need to convert it to the alphabet in terms of hexadecimal number system. So you must convert it, or else if you leave your answer this way, it means something different totally. So you need to convert it. So therefore we have 12.D base 16. So this is how simple it is to resolve a question like this. So we have come to the end of this video. Pay close attention to the subsequent videos in this channel. Alright then.